Good day everyone, and welcome to where we are putting together solutions to those problems that we are getting in math and science. This video specifically deals with the past paper questions in the area of sequences in CSEC Mathematics. We'll be looking at 5 years from May 2014 until May 2018. Feel free to like the video and add any comments down below, so we can help you in any area of math or science at both the CSEC and the CAPE levels. Let's recall the major topics in CSEC Mathematics are 10 of them, and in this video we'll be looking at the 10th one, which officially is investigation. In that area, it is tested for one full question in paper 2, which is worth 10 marks out of the total of 100. For the years May 2014 until 2018, all 5 questions in the area of investigation came on the major topic of sequences or patterns. May 2014, number 8. A number sequence may be formed by counting the number of dots used to draw each of a set of geometric figures. The first 3 figures are shown below. So let's look at diagram 1. We can see it's a 5-sided shape, which means it's a pentagon, and at each corner there is a dot, which means that for the 5 sides there are 5 dots. Now let's take a look at diagram 2. In diagram 2, it looks like an enlargement of diagram 1. It's still a 5-sided shape, meaning a pentagon, but instead of 2 dots being at the base, there are now 3 dots, and on each side there are 3 dots right around. So the number of dots increased from 5 in diagram 1 to 10 in diagram 2. And diagram 3 shows us that it has been enlarged once more. So it's still the same shape, a pentagon, 5-sided figure, but instead of 3 dots at the base, it went to 4. So the progression has moved from 2 dots on the base to 3 to 4, and it holds for every one of the 5 sides. So the number of dots in diagram 1 was 5, as we said before, and 10 in diagram 2. And as such, in diagram 3, there are 15. So part A says, draw figure 4, the next figure in the sequence, and that's worth 2 marks. So if we look at the question, we can tell that there's a progression from 2 to 3 to 4 dots at the base. So in the next diagram, diagram 4, should have 5 dots on the base and 5 dots on each side. And there are 5 sides, as it's a further enlargement, so it will be a pentagon with 5 sides as usual, and there will be 5 dots on each of the sides, which will give us a total of 20 dots. In part B, complete the table by inserting the missing information. So if we look at the table, we can see that there are 3 columns. The first being the figure F, 1, 2, 3, etc. And we have already drawn the first 4 diagrams in part A. A formula for the figures and the number of dots, n. So we can see that there is some sort of arrangement or sequence moving from the figure to the number. If we take a look at figure 1, it is 5 times 2 minus 5. And in figure 2, what has changed? The 2 has turned into 3. And in figure 3, the 3 has turned into 4. And they're giving all the correct number of dots, 5, 10, 15. And we know what it is for figure 4, but it is not required in this question. So if we look at the pattern, we can see that there's a 5 that remains constant at the beginning. So we can put 5s in the rows of figure 5 and 6, which is what we want to find. The multiplication remains the same, so we can do the same, bring down the multiplication. The 2, 3, and 4, well, that has changed. But how did it change? if we look at the numbers in the first column, we can see 1 increased to 2, 2 increased to 3, 3 increased to 4, meaning that whatever number there is in the first column, we're adding 1 to it to get the 2, 3, and 4 in the second column. As such, for figure 5, it will be 6, and for figure 6, it will be 7, and we have a subtraction sign, so we'll bring down the subtraction, and we have 5 being a constant value at the end, so we bring down the 5s. As such, we can calculate 5 times 6, that's equal to 30, 30 take away 5 is equal to 25. And then 5 times 7 is equal to 35, 35 take away 5 is equal to 30. Now, part C. Write an expression in F for the number n of dots used in the F diagram, or the F figure. So, I've put in an extra row and I'm doing it right here. So in part C, where we have F, following the pattern, the first number will be 5 times, and what goes there? Whatever we had in figure F, in the first column, we add 1 to it. So it will be F plus 1 in brackets minus 5. And that will give us n, the number of dots. Now the last part of the question, for 2 marks, part D, which figure in the sequence contains 145 dots? So, we know the formula, we've just written it in part C, that 5 times f plus 1 minus 5 is equal to n. And they just gave us the number of dots, 145. As such, we can rewrite it by substituting. So we'll have 5 times f plus 1 minus 5 is equal to 145. And of course, like every other question in math, there are many different ways to solve it. So I'll just be using one way, which I've found to be pretty simple. So if we looked on the left-hand side, we would like to be left with f alone. So we need to move things across on the right. The first thing we move across is the minus 5. So it becomes plus 5. As such, the line is 5 times f plus 1 is equal to 145 plus 5. And we can solve the right hand side, so it will give us 5 times f plus 1 is equal to 150. And now what do we move across from the left side? We move the 5. The 5 is multiplying. As such, when we carry it across, it will be the multiplicative inverse, or which means division. So we'll have f plus 1 is equal to 150 over 5, and we can solve for that. 5 into 150, that's 30. So f plus 1 is equal to 30. So what is f? We'll take the 1, which is adding, on the left-hand side, and when we carry it across, it will be the additive inverse, or subtraction, easier said. So f will be 30 minus 1, so f is equal to 29. As such, it is the 29th figure where we will be getting 145 dots. May 2015, number 8. A sequence of figures is made up of equilateral triangles, called unit triangles, with unit sides. The first 3 figures in the sequence are shown below. So let's look at diagram 1. It is an equilateral triangle, let's say of length 1, right around. And if we extract it, we'll get diagram 2, which shows that there's a progression in terms of number of triangles. So there are now 1, 2, 3, 4 equilateral triangles, or 2 layers of them. And if we extract diagram 2, and we get diagram 3 now, what does that show? It's moved from 1 layer in diagram 1 to 2 layers of triangles in diagram 2 to now 3 layers of triangles in diagram 3. So, part A. Draw figure 4 of the sequence for 2 marks. So since they gave us diagrams 1, 2, and 3, how do we progress to diagram 4? Well, each one had a different number of layers. So diagram 1 had 1 layer, diagram 2, 2 layers, diagram 3, 3 layers. As such, diagram 4 will have 4 layers of triangles. May 2015, number 8B. Study the patterns of numbers in each row of the table below. Each row relates to one of the figures in the sequence of figures. Some rows have not been included in the table. Complete the rows. and this is worth 8 marks. So you should pause the video at this point in time and attempt the question. Okay, now let's solve the question. If we look at it, we can see 3 columns. The first column telling us which figure it is. Figures 1, 2, 3, 4, which we have all drawn from before in part A. In the 5th row, we are not sure what it is, but following that will be 25 and n. And the number of unit triangles, 1, 4, 9, etc. So let's see if we can get a connection between the first column and the second. So in figure 1, there was 1 unit triangle. In figure 2, there were 4 unit triangles that made up the shape. Figure 3, 9 unit triangles. So it seems that if we take the first column and we square it, we are going to get the second column. So 1 squared is 1, 2 squared, 2 2s are 4, 3 squared, 3 3s are 9. As such, if we're following that pattern, for figure 4, 4 squared will be 16. And if we check back in part A, our construction of the 4th figure, we would find 16 triangles. So our method seems to be working. So in the next row, which figure number when squared will give us 144? Or we could say that differently. What is the square root of 144? And that is 12. And in the next row, for figure 25, it will be 25 squared. And we have our calculators, and that will give us 625. And in the last row, for n, for any figure, then it will be n squared. So we've completed the first and second columns, and we only have the third column to complete. Let's look at the pattern. We can see coming down vertically, as we've done before in previous questions. We look to see what remains the same. We can see that there are brackets throughout. There's a division sign throughout as well. So the first element or item or number in the first brackets is 3. And if we go into second row, it's 3, and third row 3. So we can continue for the other 4 rows, putting in 3's there. And what comes after the 3? Multiplication sign. So we can include 4 multiplication signs coming down below in the rows of figure 4, 12, 25, and n. Now, let's take a look at what comes next. We can see 1 in the first row, 2 in the second row, 3. So it's changing. And where are we getting these numbers 1, 2, and 3? From the values of the figure in the first column. So in figure 4, what number will it be? It will be 4. And then 12, as it follows into the figure 12. In figure 25, it will be 25. And for any number n, it will be n. So we've completed the first set of parentheses or brackets. Let's look at the second set. It starts with 1 in the first row, 2 in the second row, 3 in the third row. Remember, we're only looking at it vertically downwards. So we can see if we find a pattern. As such, where did we get 1, 2, and 3? It's a repetition of the first column of the figures. So what follows will be 4, 12, 25, and n. And what goes next? The addition sign. So we can put 1, 2, 3, 4 addition signs. And we're adding what? We're adding the number 1. So we can put 4 ones in there as well. And that was the numerator. In the denominator, it remains constant. We can see in rows 1, 2, and 3, the denominator is 2. So for the next 4 rows, we put 2 in at the denominator. Now we put our equal signs because we can solve for 4, 12, 25, but we can't solve for n. So we leave it as is for n. So let's solve now. We have our calculators, we can work this out, or we can say 3 4s are 12, 2 into 12, 6, 6 times 5 is 30. And similarly solve for the others, we'll get 234 and 975. May 2016, number 8. The diagram below shows the first 3 figures in a sequence. Each figure is made up of nuts and strings. Each nut connects exactly 3 strings. So let's look at diagram 1. We have a string on the left with a nut connected to it, and then 2 more strings going to the right of it. Let's extract diagram 1 in order to produce diagram 2. We can see on the right hand side of the red strings, there are added a pair of green strings each. So in the first diagram we had 3 strings and 1 nut. In the second diagram we now have 3 red and 2 and 2, 4 green, so that's 7 strings and 3 nuts. So let's extract diagram 2 in order to produce diagram 3, and we see at the end on the right of all the green strings, and there are how many ends? 1, 2, 3, 4. On the 4 ends, another pair of strings are added. So we now have 3 red, 4 green, and 8 black. So that's a total of 15 strings. And how many nuts? 1 with the red, 2 with the green, and 4 more. So that's 7 nuts. Part A. Draw figure 4 of the sequence. So let's extract diagram 3 as before. And if we look at the end where the black strings end, there are 1, 2, 3, 4, 5, 6, 7, 8 ends. On each of these ends, we will add a pair of strings. So we have 8 pairs of strings coming on as well. May 2016, number 8b. The table shows the number of nuts and strings in each figure used to draw figures 1, 2, and 3. But let's recall that in part A, we also drew figure 4. So we also have those values. Instructions are complete the table by inserting the missing values in the rows. So if we look at the first column, it gives us which figure number it is. Figure 1, 2, 3, 4 up to 10. And then in the second column, the number of nuts. And we can tell from our diagram that in the first figure there was 1 nut, 3 in the second figure, 7 in the third, etc. And of course we could count the fourth one and we will get 15. And let's see what pattern there is. So 1, 3, 7, 15 doesn't really look like a pattern that we recognize. However, if we add 1 to each one of them, then the number of nuts in the first figure will be 2. The second figure will be 4, 8, 16. So let's see. That sounds a little familiar. So let's look at this table that we're adding on the side to see if it helps us. 2, 4, 8, 16, 32, 64, which means 2 to the power 1, 2 to the power 2, 2 to the power 3, etc. up to 6. And if we continue, we could go from after 64, 128, 256, all the way up to 4096. So 2 to the power 7, 8, 9, up to 12. So that looks like the pattern that we have. As such, if we look in the the second column, where we have 1 is equal to 2 minus 1, what we can say 2 can be replaced by 2 to the power 1 minus 1. And then for 3, which is 4 minus 1, that is equal to 2 to the power 2, 2 squared, minus 1. And for 7, 8 minus 1 is equal to 2 to the power 3, 2 cubed. Remember, 2 times 2 is 4, times 2 is 8. So 8 minus 1. And for 15, where we have 16 minus 1, that will be 2 to the power 4 minus 1. So it seems that we have a pattern. So if we recognize that, and we're looking down, we see 2 to the power 1, 2 to the power 2, 3, 4. Minus 1 in all of them. The minus 1 isn't changing. What is changing is the 1, 2, 3, 4. And where do we get that? From the first column. From whichever figure number it is, we can say that it is 2 to that power. As such, we could go down to look at figure 10. Figure 10 will then be 2 to the power 10 minus 1. And if we look at our little table on the side, 2 to the power 10 is 1024. So we can see that is equal to 1024 minus 1, which is 1023. Right. So we solved most of the second column except for the missing values there. So let's look at number of strings. And let's see if there's a pattern there as well. So there are 3 strings, if you recall, in the first diagram. and then 7 strings. And if we check the number of strings in the third figure, we would see 15 and then 31. So what pattern is there? Well, if we add 1 to all of them, it looks familiar. 3 plus 1 will give us 4. And we add 1 to the 7, we get 8. So we get 4, 8, 16, 32. So it looks like the table we wrote on the side. Except 4 will be 2 squared minus 1. Right? So 7 will be 8 minus 1, which is 2 cubed minus 1. 15 is 16 minus 1, which is 2 to the power 4 minus 1. 31 is 32 minus 1, which is 2 to the power 5 minus 1. So if you look at the pattern, the minus 1 doesn't change coming down. The 2 doesn't change. It's the power of the 2. So it changes 2, 3, 4, 5, etc. As such, where are we getting those numbers from? Look at the figure in the first column. Figure 1, 2, 3, 4 has increased by 1. So figure 1 becomes 2 squared, figure 2 becomes 2 cubed, figure 3 becomes 2 to the power 4, etc. That means for figure 10, it'll be 2 to the power 10 plus 1, which is 2 to the power 11 minus 1. And if you look in our table, 2 to the power 11 is 2048. So it's 2048 minus 1, which is equal to 2047. So we've finished the last row. The row before it, the second to last row, or the penultimate row, says that the number of strings is 255. So 255, how do we get that? It will be something minus 1. And what number will that be? 256. So 256 minus 1 will give us the 255. And if we look at our little table on the side, 256 is 2 to the power 8. So 2 to the power 8 minus 1. Now let's recall, if it is the number of strings is 2 to the power 8, then the figure would be 1 less, following from the pattern. So that would be figure 7. And if we know that the figure is 7, then we can solve for the number of nuts. The number of nuts would be equal to 2 to the power 7 minus 1, which is equal to 128 minus 1, which is 127. May 2017, number 8. The first 4 figures in a sequence are shown below. Figure 1 is a single dot, while each of the others consists of dots arranged in an equilateral manner. So let's look at diagram 1. 1 single dot. Diagram 2, as we extract it, will give us the 1 single dot and 2 more below it. So there's 1 and 2. 3 dots in diagram 2. In order to get diagram 3, let's extract diagram 2. And we already have 1 and 2 dots, and we add another layer below with 3 dots in it. Now, let's extract diagram 3 to get diagram 4. So we already have 3 layers of dots, and to get diagram 4, we add a layer below with 4 dots. So hopefully we can see the pattern. Diagram 1 has 1 dot, diagram 2 has 2 dots in the bottom layer, diagram 3 has 3 dots in the lowest layer, diagram 4, 4 dots. So part A, draw figure 5 of the sequence. So let's extract diagram 4 to create diagram 5. So we already have 1 and 2 and 3 and 4 dots. So diagram 5 would mean we're adding 5 dots at the base. So part B, how many dots would be in figure 6? Well, if we look at the pattern, figure 6 will have 1 in the top layer, plus 2, plus 3, plus 4, plus 5, plus 6 dots. And that will give us 21 dots. May 2017, number 8. The table below refers to the figures and numbers of dots in each figure. Study the patterns shown. So if we look at the table, we can see there are 3 columns. The first being figure N, which is labeled 1, 2, 3, and we have dealt with these first 3 diagrams in part A. And now they give us a pattern, the number of dots D in terms of N. So we can follow this pattern in order to move from which figure it is to give us the total number of dots used in the diagram, which is the third column. So if we look at the first row, figure 1, we see the pattern is a half times 1 times brackets 1 plus 1. So let's work it out. 1 plus 1 is 2. 1 2s are 2. Half of 2 is 1. So the number of dots used in first diagram is 1. And if you check back in part A, our first diagram, it had 1 dot. Similarly, for the second row, it's a half times 2 plus 1 in brackets. So a half of 2 is 1. 1 times the brackets. The bracket is 2 and 1 is 3. 1, 3 is 3. So the pattern works. And we can see, following the pattern coming down vertically, that what remains constant is a half. So we can put in a half as we come down. Part C says, complete the row which corresponds to figure 11 in the table. So if we're completing part C, that means we have to include a half, and the multiplication is constant in figures 1, 2, and 3, so we bring down the multiplication as well. And what else is constant? The brackets. So we'll bring down the brackets as well. And there's an addition of 1 for figures 1, 2, and 3. So we'll do the same, bringing down add 1. So what is changing? 1, 2, and 3. If we look at that, and where are we getting 1, 2, and 3? In both cases, the one on the outside of the brackets and the one on the inside of the brackets, those are changing, and they are getting those values from column 1. So if we're looking at figure 11, then it will be a half times 11 times 11 plus 1. And we can solve this. We have our calculators, or we can work it out as is. 11 plus 1 is 12. A half of 12. 2 into 12 is 6. 6 times 11. 6 11s are 66. And we've solved part C. In part D, determine which figure in the sequence has 210 dots. So we know generally that what we're going to do here might be easier to work out part E first. So let's look at that. Write a simplified algebraic expression for the number of dots D in the figure N. So we look at the row E, there, the last row in our table. For figure N, for any number, then what is the pattern? A half, because it's the same coming down, times, again, or multiplication. And it's not 1, 2, 3, or 11, it's any number from the first column. So we use N times brackets N plus 1. And that will give us D. So if we know this formula, D is equal to a half times N by N plus 1. And they're telling us in part, let's go solve part D now. Then what do we know? 210 is equal to a half times N plus 1. So if we're solving there, I could carry the half across. The 2 is dividing on the right hand side. When I carry it across on the left, it will do the opposite of that, right? Which will be multiplication. So 210 times 2 is equal to N by N plus 1. And 210 times 2 is 420. 420 is N times N plus 1. So let's recall, what does N times N plus 1 mean? It means any number multiplied by the number that's coming right after it, the consecutive number. So if it's 2, it's 2 times 3. If it's 10, it's 10 times 11. Or if it's 12, it's 12 times 13. So to give us an idea of where that falls, let's imagine it's N times itself. That'll be like N squared. So if 420 was really N squared, what would N be? The square root of 420, which works out to be 20.49. Now that gives us an idea that somewhere along there would be N and its consecutive number N plus 1. So let's try it. Let's try, since the answer we got for the square root of 420 is 20.49, let's try 19 and 20. So 19 times 20 is equal to 380. So that didn't give us it, but we're close to 420. So let's go up a little more. So let's write 20 times 21. Remember, its consecutive numbers is N times N plus 1. 20 times 20 plus 1 is 420. So we've gotten our solution. What does that tell us? That N is 20, meaning that is the 20th figure will give us 210 dots. Right. Let's solve for part F, the last part of the question. Show that there is no diagram that has exactly 1,000 dots. So since we have a formula already that D is really equal to a half times N plus 1, We can use that just as in parts D. So 1000 is equal to half times n plus 1. Let's do something similar. Carry the half across. So 1000 times 2 is equal to n times n plus 1. 1000 times 2 is equal to 2000 is equal to n times n plus 1. So pretty much we could use the same format like we did before. I'm trying to use something similar so it's easy for you to follow. So the square root of 2000 is 44.72. So it means that n should be close to 44.72. So let's try 43. So 43 times the number that comes right after it is 44. 43 times 44 is equal to 1892. So it doesn't give us 2000 yet. A little too small. So let's increase it. So let's try n as 44. So 44 times 45, the number that's after it, and that gives us 1980. So we're getting closer to the 2000. So what is telling us? The 43rd figure, if we drew it, required 1892 dots, while the 44th figure required 1980 dots, some even more dots. So let's try the 45th figure. The 45th figure will be 45 times 46, which works out to be 2070. What does that mean? It means to say that we got nothing that's giving us 2000. We're either getting more or less. So there's no diagram that actually gives us the number of dots that's required. May 2018, number 8. A sequence of figures is made from squares of unit length. The first 3 figures in the sequence are shown below. So let's look at diagram 1. We can see that there are 3 unit squares formed in the shape of an L, right? 2 horizontal and 1 above it. And if we extract it and show diagram 2, the difference is that there are 2 more vertical squares are added. We have them in yellow, so we can see the growth. And if we extract diagram 2 to diagram 3, we will see 2 more again added vertically upwards, which we have in green. So we can see the progression. So part A, draw figure 4 of the sequence. So what we'll do, we'll take diagram 3 and extract it to give us diagram 4, which means what's the growth? We had 2 yellow squares and then we added 2 green squares. So now in diagram 4, we'll be adding 2 blue squares, and that is our 4th figure. May 2018, number 8b. Study the pattern of numbers in each row of the table below. Each row relates to one of the figures in the sequence of figures. Some rows have not been included in the table. Complete the rows. So if we look at the table, we have 3 columns, the first being the figure, numbers 1, 2, 3, 4, which we have drawn in part A, and number of squares in the figures. We're given 3, 5, 7, and somewhere down the road, 43, for some particular figure which we need to find, and perimeter of the figure P, 8, 12, and 16 for the first 3 figures. So we need to solve. Well, the first thing we can do is we can create a formula for any figure. So let's look at the last row for figure N, right? And let's see if we could come up with that. So let's look at the pattern. We have 3, 5, and 7. So that means we're adding 2. 3 and 2 is 5, 5 and 2 is 7. So we keep adding 2. That's the pattern. So if we go backwards from 3 to an initial value as if there was some figure before 1, then that would be 3 take away 2. Just how we added 2 going down, we'll minus 2 coming up. So 3 take away 2 is 1. So we can say, how do we get figure 1? 1, that's what we started with, add 2. And how do we get figure 2? 1, add 2, add 2. That'll give us the 5. Figure 3, 1, add 2, add another 2. So that will give us 7. So we're seeing a little pattern here. Let's see if we can write that a little shorter. In the first case, it will be 1 plus 1, 2, 1 times 2. In the second case, it will be 1 plus 2 times 2, because there are 2 2's there, and that'll still give us a 5. In the third case, figure 3, it'll be 1 plus 3 2's. So if we follow that format in figure 4, it'll be 1 plus 4 2's and 4 2s are 8 and 1, that will give us 9. And for n, for any number figure, then we say 1 plus n times 2. How do we get the n? Let's recall that inside the brackets we have 1, 2, 3, 4 coming down. That's the only thing that's changing in the pattern as we go down in the first 4 figures. And where are we getting 1, 2, 3, 4? From the figure column, 1, 2, 3, 4. So if we have for any figure n, then it'll be 1 plus n times 2. So similarly now, we can use that in order to solve for 43 for that figure. So we know the general rule, S, which is the number of squares, is equal to 1 plus n times 2. And in this case here, S is 43. So 43 is equal to 1 plus n times 2. We can take the 1, which is on the right-hand side, which is adding, and carry it across. The additive inverse, or subtraction, means the same thing. So 43 minus 1 is equal to n times 2. So 42 is equal to n times 2. We want to solve for n, so we need to remove the 2 from the right-hand side. It is multiplying. When I carry it across, the opposite of multiplying is multiplicative inverse or division. 2 into 42 is equal to n, so n is equal to 21. As such, it's the 21st figure which will give us 1 plus 21 times 2. 21 times 2 is 42 and 1 is 43. So it works. So let's go now and look at the perimeter. So if we follow the format from as the squares and we look at the perimeter values now, 8 is increasing by 4 to give us 12. It's increasing by 4 again to give us 16. So that means that if we're going backwards, we would be subtracting 4 each step upwards. So if there was a figure before figure 1, right, then it would be 8 minus 4, which will be 4. As such, figure 1 can be written 4 plus 4. And figure 2, 4 plus 4 plus another 4. Figure 3, 4 plus 4 plus 4 plus another 4. So that could be shortly written as 2 4s, 2 times 4, which is 8, 3 times 4, 12, 4 times 4, 16. So we can see a pattern. The times and 4 is remaining the same, but the 2, 3, and 4 is what is increasing. And where is that coming from? It's coming from column 1. If we look in column 1, we had 1, 2, 3. It became 2, 3, 4. That means each figure number increased by 1. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So for the row 4, for figure 4, it'll be 4 plus 1 is 5, 5 4s are 20. And it makes sense because even if we add 4 to 16, we'd still get 20. Now, if we need to get for the 21st figure, it will be 21 times 4, which is 84. And finally, for n, then we can say it'll be n plus 1 times 4, and that will be the pattern. Now, part C of the question says, determine the relationship between the number of squares S and the parameter P of a figure. So, if we look at the number of squares, look at the values, 3, 5, 7. How does it become 8, 12, 16? Well, let's see. Let's double the values of the squares. So 3 will become 6, 3 2s are 6, 5 2s are 10, and 7 2s are 14. So now let's compare 6, 10, and 14 to 8, 12, and 16. Now what's the difference? When you take the 6, we add 2 to it to get 8. 10, add 2 to it to get 12. 14, add 2 to it to get 16. As such, to get P, the parameter, we are taking S and we're multiplying by 2. So that's 2S and add 2. And that will be the relationship between the parameter and the squares. P is equal to 2S plus 2. This brings us to the end of the second video in this series on past paper questions in CSEC Mathematics, specifically sequences. In the first video, we completed the past paper questions from May 2009 to 2013, and in this one from 2014 to 2018. In our third video in this series, we will be continuing from May 2019 onwards.